Welcome back to LectureCast-Prolog. So far we have treated Prolog as a declarative language. You describe what is true, and the engine finds the answers. That is mostly true. But the engine reads your program in a definite order, top to bottom, and left to right, and that order has consequences. In this module we will see how the very same clauses, simply reordered, can change which answer comes first, how fast you get it, and even whether the program stops at all. Order matters. Let us connect this to what you already know. In Module 3 you met the engine, unification, depth-first search, and backtracking. In Modules 4 and 5 you learned recursion, a base case, and a recursive step that shrinks the problem. Today nothing new is added to that machinery. Instead, we look closely at the machinery's habits. The engine always tries your clauses from the top down, and it always solves the goals in a rule from left to right. When two orderings describe the same logic, those habits stay invisible. When they do not, order decides everything. Every Prolog clause can be read two ways. The declarative reading asks, what does this say is true? Ancestor of X and Y holds if X is a parent of Z and Z is an ancestor of Y. The procedural reading asks, how will Prolog actually search? It tries this clause, solves the first goal, then the next, backtracking when something fails. When the two readings agree, you can ignore the procedural one. The trouble starts when a clause is declaratively correct but procedurally disastrous, perfectly true, yet it loops forever. To write Prolog that runs, you must hold both readings in your head. Here is the rule the engine never breaks. Clauses are tried in the order you wrote them, from the top of the file down. Within a single rule, goals are solved from left to right. The search is depth first. Prolog dives all the way into the first goal before it considers the next. And whenever a goal fails, it backtracks to the most recent choice point and tries the next alternative. For simple habits, top down, left to right, depth first, and backtrack on failure. Everything in this module is just a consequence of these four. Keep them in front of you. Start with clause order. Suppose two clauses both succeed. Because Prolog tries them top to bottom, the one you wrote first produces the first answer. Swap the two clauses, and you get the same set of solutions, but in a different order. For a query that asks for just one answer, that difference is everything. And if your recursive clause sits above your base case, Prolog will keep diving into recursion before it ever checks whether it can stop. Same logic, same answers on paper, but a very different experience at the prompt. Clause order is the first lever. Now the example that makes this unforgettable, and it uses the ancestor predicate from Module 4. There are two ways to write the recursive rule. The left-recursive version puts the recursive call first, ancestor of X and Y if ancestor of X and Z, and parent of Z and Y. It is perfectly true. But watch the search. To solve ancestor, Prolog first tries to solve ancestor again, with nothing yet narrowed down, and again, and again. The goal stack spirals downward forever. The right-recursive version puts parent first, parent of X and Z, then ancestor of Z and Y. Now each step takes a real parent step down the family tree, the problem shrinks, and the search reaches an answer. Two true rules. One loops, one works. The only difference is order. Clause order chooses which answer comes first. Goal order, the order of the conditions inside a single rule, controls how hard Prolog works to find it. Imagine a rule with two goals. One searches a huge space of candidates, the other is a cheap test that most candidates fail. If you write the big search first, Prolog generates every candidate and tests them one by one. If you write the cheap test first, it rules out the impossible candidates before the expensive search even begins. Same answers, but the second ordering can be orders of magnitude faster. The rule of thumb, put the most restrictive goal first. Goal order does not only affect speed, it can decide termination. A recursive goal needs its arguments to be shrinking toward the base case. If you place the recursive goal before the goal that actually narrows it down, the recursive call fires with its arguments still wide open, and the search runs without bound. Move the narrowing goal in front, so the argument is constrained before the recursion runs, and the same predicate terminates. The lesson generalizes the ancestor example. A recursive goal should come after a goal that makes the problem smaller. Let us picture goal order as shaping the search tree. The generate and test pattern builds a wide tree of candidates and only prunes at the leaves, where the test finally runs. Each candidate is fully explored before it is rejected. Move the test to the front, test and generate, and the tree is pruned at the top. Impossible branches are cut before Prolog ever descends into them. The set of solutions at the bottom is identical, but the amount of tree you walk to reach them collapses. Reordering goals does not change what is true, it changes how much of the search you actually pay for. This brings us back to a rule from Module 4, with a sharper edge. We said, always write a base case. Now add, put it first. When the base clause sits above the recursive clause, Prolog checks whether it can stop before it commits to going deeper. The program is easier to read and, for some queries, far less likely to wander. A recursive first ordering can still be correct, but base first matches how you want the search to behave: stop when you can, recurse only when you must. Small habit, big payoff in clarity and safety. The trap behind the ancestor disaster has a name: left recursion. The warning sign is a clause whose first goal is a recursive call on an argument that has not yet been narrowed. Because the engine solves left to right, it re-enters that recursion immediately, with nothing smaller to work on, and never returns. Once you can spot the pattern, the fix is almost mechanical: put a goal in front that consumes a piece of the input or takes a concrete step, so that by the time the recursive call runs, the problem is strictly smaller. Recognize it, and reorder. Let me show you the two outcomes side by side as a goal stack, the engine's to-do list. With the left recursive rule, each call pushes another copy of the same unshrunk goal on top of the stack. The stack grows, and never drains. That is the infinite loop, and eventually the stack overflows. With the order fixed, each call first takes a real step that shrinks the problem, so each new goal on the stack is smaller than the last. The stack rises a little, then drains down to the base case, and the search stops. A stack that grows without bound, versus a stack that drains to the base, that is the whole difference, and it is decided entirely by order. Let us collect the working rules. Put the base case first, so the engine can stop before it recurses. Place a recursive goal after a goal that shrinks the problem, never before. Inside a rule, lead with the most restrictive, most bound goal, to prune early. And remember the deepest lesson: declarative correctness is not the same as termination. A rule can be perfectly, logically true and still loop forever. To write Prolog that runs, reason about what is true and about how the engine will search for it. Both readings, every time. So, to recap. The engine reads clauses top to bottom and goals left to right, depth first, backtracking on failure. Clause order picks which answer comes first, goal order controls efficiency and termination. Left recursion is the classic infinite loop, and the cure is to put a shrinking goal first. Above all, a clause can be true and still not stop, so reason procedurally as well as declaratively. You can now see the search tree clearly. Next time, in Module 7, we will learn to control it directly: the cut, which commits to choices and prunes branches on purpose, and negation as failure. See you there.